works best, obviously, in sedimentary rock. You know, if you were drilling through a basalt or something like that, it could potentially give you false magnetic indicators, because like gravity, you know, if we think of magnetics like gravity, it essentially has a similar type of resolution. It's a smooth result, and so there are multiple solutions to the same magnetic susceptibility contrast. So if you're far away from that hole, you can actually go the wrong direction, or partially the wrong direction. And the reason that you're able to hit it is that you keep making measurements, as Fred said, and you kind of steer your way right toward that hole. So by the time you're a few feet away, you kind of know which direction to change in order to hit that magnetic anomaly. So a little bit of history. Magnetics is actually the oldest branch of geophysics. The Egyptians described magnetic repulsion well before the birth of Christ. And the Chinese had actually found lodestone and looked at a needle, something metal attracted to lodestones. By 1000, they were using compasses. And in 1600, Gilbert actually theorized that the Earth itself was a bar magnet with a North Pole and a South Pole. Then obviously in the 19th century, we got to the relationship between electricity and magnetism, and now oftentimes we talk about electromagnetism. Prior to that, we thought that the magnetic field was independent. Faraday actually showed that there was a relationship between the electric field and the magnetic field. And there's a great quote from Faraday, but I think he was talking to Queen Victoria in the 1840s. And Queen Victoria said, so what use is this electromagnetism that you've discovered? And he responded and he said, well, of what use is a baby? And that was really the beginning, if you will. It wasn't the beginning of the industrial age, but it grew in a corresponding sense to the industrial age. We had, well, the electric light bulb. Everything became electric in the 19th century. Well, we actually began prospecting. We actually used geophysics in Sweden in the mid-1600s. We actually started producing magnetometers in the 1870s. And these magnetometers became kind of ubiquitous by the early 1900s. And now it's one of the least expensive and easiest to acquire geophysical data sets. It can be acquired on land. It can be acquired in the air. Obviously, running an airplane is still pretty expensive. So what do we do with it? Well, obviously metal detection. We're talking about looking for, primarily for tanks and pipes and anything real shallow. We can also use it to look for groundwater and contaminants in some cases. Anything in archaeology that has metal associated with it. Buried walls, tunnels, old fire pits, tombs, as we talked about earlier, old shipwrecks. There's a number of great examples from the Missouri River, where they actually ran magnetometers up the Missouri River looking for sediment-buried gunboats from the Civil War that were going up and down. So anything with iron is really going to have this response. As I said before, we can look at the depth to magnetic basement and basins. That's going to have oil and gas and groundwater application. We can look at the detection of faults. We actually did this for one of our field surveys a few years ago up in the White Mountains of Nevada. Faults oftentimes are conduits, and they've flushed out magnetic materials. So if you find faults, you're actually looking for a negative magnetic anomaly in some cases. As we talked about the very first day of class, magnetics were a major player in the discovery of tectonic processes, right? The spreading centers that we saw were associated with magnetic anomalies. And finally, we're using magnetics in a lot of planetary science these example of that, here's a picture from the Mars Global Surveyor of the Mars crustal magnetism, and superimposed on the crustal magnetism is the topography of Mars. So let's go really briefly into the forces associated with magnetism. So this picture looks eerily like gravity. Okay? We've basically got a force in the R direction. We've got a force that's inversely proportional to radius. And we've got the equivalent of M1 and M2. So what are those in magnetism? What replaces, from your basic physics, what replaces mass in the force of magnetism? Charge. It's charge strength, exactly. So P is equivalent to M. KE, what's that? That's a constant, kind of like our gravitational constant. But the interesting thing about KE is that KE depends on the material. Okay, so KE is no longer a constant for all materials. In order to find the force of magnetism, we actually have to understand what the medium is in which the charges are attracted. So if we're looking at a vacuum or free air, actually air or water, the charges have a certain KE. And as we change the medium to rock or basalt or something like that, the charges will have a different KE. So just like in gravity, a gravity field, we can take the force of gravity and we can divide it by one of the charges. Maybe this we're dividing by our magnetometer response at the surface, the magnitude of the magnetometer. And so we get a field strength, and this is typically given in nanoteslas. And we'll talk about the magnetic field of the Earth in terms of nanoteslas. Now, let's go down. We've looked at this, I actually discussed this, but let's go over it again. Again, gravity is just M1, M2. G is a universal constant. The difference between gravity is that we have 2-point monopoles, just like we have 2-point masses. The strength of the monopole causes the force of magnetism. And the Coulomb constant is related to the magnetic permeability, which is not universal and varies with the medium. The permeability is 1, or the relative permeability, we're going to compare different permeabilities, is 1 in air and water. So, magnetic fields are like gravity fields. Again, there's only a few differences. If we had a point monopole, it's exactly identical. And again, we have a constant that's a function of the medium. We're looking here at mu naught, which is air or water. So, what's the difference? Well, each point charge has a different characteristic of gravity. Remember, gravity is always attractive, right? The field lines of gravity always point in toward the center of the Earth. In magnetics, in a bar magnet, we have one point charge that is attractive, the other that is repellent. So when we put these 2-point charges together, we get a magnetic field that is more complex than a gravity field, in that it not only has a magnitude, but it changes with direction, right? At the poles, if we look at these perpendiculars, can you see these things right here? These lines coming out? At the poles, the gravity looks, or the magnetics looks exactly like gravity, because the change depending on where we are. If we had a surface of measurement here, we'd see that the field lines are going to change depending on the surface. So how do these field lines change depending on where we are on the surface? Let's go past this for a moment. Here we go. Okay, so to get the field lines, all we do is add up the vectors in certain directions. So we have a positive force, a negative force. We get a vector response that is perpendicular to the point monopole, attractive and repelling, and then we simply add up the vectors to get the field lines at any position around those two point monopoles. And let's see, I'm going to go down to here. There's a lot of this. I'll be going back through this in a second, a little bit. I kind of bounce around here. All right, let's derive the dipole field. Okay. So let's say we have a point of measurement out here, all right? And we know that we're going to generate the magnetic field, which